this video we're going to discuss equilibrium. In equilibrium we are going to see that we have a situation which is stable, yet we have forward and reverse processes occurring at the same rate. If we look at a typical reaction that we've done, let's look at just some gas A and some gas B are going to react to form gas C and gas D. Here's our reactants, here's our products. And we said these things are going to collide, I get these products. I start with this, I end with this. And let's look at it as an elementary reaction. So I've got particle A is going to hit and collide with particle B. And I get the reaction, here's my products. So I start with some container, and I put, in fact I've got about 8 particles of A in this box. And I'm just going to start with some kind of random number. I'm going to say I put 5 particles of B. So I've got 8 A, 5 B. And up until this point, we've been saying, okay, this reaction is going to continue until something runs out. In this case, it's 1 for 1, and so I've got less B. So this reaction would continue until I run out of B, and then the reaction stops. But we're going to look at these situations. Let's say in this particular reaction, A will collide with B, create C and D. But the reverse is also possible. Let's first look at this as an elementary reaction. The rate law for this reaction, it's an elementary A hits B, which means it's first order to A and first order to B. So the rate for this is equal to some rate constant K times the concentration of A to the first power times the concentration of B to the first power. So it's first order to both. So I put this mixture in, and this is going to be at time equals 0. I put this mixture together, and the reaction starts. So what happens at this point? I get that. I get A plus B are going to start to collide, and when they collide just the right way, they make C plus D. Let's look at it now a little bit later. Time equals 1 minute later. So here, 1 minute later, I check my container and I see this is what I've got. What I've created is I've dropped down to, right now I have of A, I have 6 particles. Of B, I'm down to 3. I've added, since every time 1A and 1B react, I get 1C and 1D. So 2 have reacted. So of C, I have 2 particles. And of D, I have 2 particles. So these are my numbers as I check this thing later. But now in this particular reaction, what can happen is these C and D reactions, they don't just stay C and D. I've got a reversible reaction. What I can have occurring is C and D can react, and the reaction can go in the reverse direction. Okay, so when we first began, all we had was the forward reaction. A and B collide, create the product C and D, and we have our rate law first order since it's an elementary reaction. But once I get some C and D present, so I've created some. Now this reaction has continued for a minute. I've created some C and D. Now that I've got some of those present, C and D can collide in an elementary reaction to make A and B. So my products can now become reactants again. So the reverse reaction in this case is possible, and many chemical reactions are capable of doing both the forward and the reverse reaction. So as soon as I start to build up some of these products, some of the products will react to make the reactants again. Elementary reaction, therefore, the rate will be some constant times the concentration of C times the concentration of D to the first power, since it's an elementary reaction. Since this is the forward, I wrote this one as the forward. Let's just put a little subscript. Rate forward is equal to this. Its constant will not necessarily be the same as the constant for the reverse. It depends on a lot of different things. This will say that the rate reverse is equal to some different constant. We'll call it Kr times the concentration of each of the products. So we're checking our container. And so at time equals 1 minute, these were our concentrations in particles. And then what's going to happen is the reactions are going to continue. I still have A and B present. I now have C and D present. So these reactions will continue. I will get A and B reacting to make C and D. But now that I've built up a little bit of C and D, I'm going to get some of the reverse reaction. At first, because the reaction rate is dependent on the concentration, my initial reaction for C and D is they just are starting to build up. That reverse rate is not going to be as fast at first. While their concentrations are still fairly low, this is going to be slower. The reverse reaction will be happening slower. So I'm going to check my my chamber again a minute later. I check all my number of particles for a minute later. So at time equals 2 minutes, what's happened is my amounts of A and B are starting to drop. My amounts of C and D are starting to go up, so that the forward reaction is beginning to slow down a little bit. The reverse reaction is starting to speed up. So I look at it here and I find that A, there are 5 particles. B is down to 2. And C and D have increased to 3 particles. So now if I check this reaction, what has happened in my reaction? I'm going to get to a point, at some point my amount of C and D increases enough that the concentration, that this rate will start to speed up. As I get more and more C and D, the rate starts to speed up. This rate will slow down until I get to a point where they become equal. So the reaction continues. I get A and B making C and D. I get C and D making A and B. As soon as I get to that point where the rates are equal, my concentrations aren't going to change anymore. Let's say at 2 minutes I reached that point. At 2 minutes I got to that point where now A will make B, A and B will make C and D at the same rate that the reverse reaction happens. I'm still going to get these reactions happening continuously, but nothing changes inside. The concentrations or amounts of the different elements does not change over time, because at the rate I make this, I also get the same rate of reverse. So if I check this 3 minutes later, what I find is the same amounts of the particles. So it looks like nothing changes, like it just stopped reacting, but it did not in fact stop reacting. What happened was A and B hit make C and D, C and D hit make A and B. They're happening at the same rates, so the amounts of what's in the chamber will remain constant over time now, even though the reactions, there's still a lot of collisions going on and the reactions are proceeding. Forward and reverse rate, we call that equilibrium, because everything remains constant and steady unless we do something to change the circumstances. If we were to graph, let's say we're going to graph the amount of each substance over time, either the amount or the concentration. What again, I'm checking A, I'm going to check B. I start at time equals 0. I start with some A and B. I didn't have any C and D left. This is C and D. They're both the same since I started, since they're made one for one. So what happens is A and B are going to drop, C and D is going to gain. Nothing runs out, but I get at some point I get this stable condition, and then at this point where everything's stable, that becomes equilibrium. At equilibrium, I have a very dynamic situation, reactions continuing back and forth, but all my concentrations, all of my amounts are staying the same. Let's take a look at now, let's write our equilibrium expression or turn it into a rate law. Okay, so this was our rate law for the forward reaction. I've got it first order, I made an elementary reaction of A and B, a collision of A and B. So first order to A, first order to B going forward. In the reverse direction, I have first order to C and first order to D with different rate constants. At equilibrium, when I get to that equilibrium point, the rate of the forward reaction equals the rate of the reverse reaction. So I'm just going to sub in, rate of forward is this, rate of reverse is this. And I've substituted that expression. What I want to do is come up with a constant. So what I'm going to do is I'm going to put both my constants on the same side. So I'm going to divide both sides by A and B. I'm going to divide both sides by KR. That'll take this out, that'll take this out. And I get that this constant, because here's a constant divided by a constant, which is a constant, is equal to the concentration of each of the products divided by the concentration of each of the reactants. This has a special meaning. It is called the equilibrium constant, KEQ. KEQ is the abbreviation, so I've now taken a capital K instead of these lowercase k's for rate constants. This is called the equilibrium constant. And it gets this capital K. And these equilibrium constants become very important because they allow us to change the concentrations of the initial and predict what our concentrations will be at equilibrium. In fact, there's a general expression for the equilibrium constant. I'm going to take any reaction. This applies to all reactions for equilibrium. I'm going to take now, instead of a coefficient of 1, I've got any coefficient. It could be 1 or anything else. Now they have various coefficients. KEQ, at equilibrium, there will be a constant value that depends on it will depend on the concentration of reactants raised to the power of the coefficient, and that will be divided into the products raised to the power of the coefficient. So it is products over reactants. So, and this general expression applies to all reactions at equilibrium. And these equilibrium constants are going to be what we work with quite a bit in this course.